My name is Andrew Smith of Bentley Systems, and I will be joined later in the presentation by Leif Johnson. The topic of today's tech talk is From Data to Information, how to use big data to maximize rail ROI. The first thing we need to do is have a quick look at the distinction between data and information. So data, typically in any decision-making process, is the starting point. The data we could be looking at if we're working in rail operations, for example, can be measurements, it can be inspections, it can be basic facts, documents. This data that we have available to us contains a wide range of information. The information that is actually within the data is then in turn used to actually support decisions that are used to be able to drive value, reliability, and safety in the assets. So as you can see, it's critical that if we don't start with the right data, we can't derive the correct information from it, which in turn means we're going to make less than optimal decisions about how we're going to design, construct, or operate our rail assets. When we look at data, there are a number of different measures associated with it. The most common ones that I encounter in my experience are the currency of that data set. This is a measure of how recent the data actually is. Now, it doesn't necessarily mean that the data has to be perfectly up to date. What is critical here is that the data is of a fit-for-purpose currency relative to the tasks that are actually being performed. The next measure we're looking at is a completeness measure. This is whether the data set we're looking at actually covers the entire asset. So if we're looking at data related to signals, for example, we want to have a consistent data set covering all of the signals within the rail infrastructure we're looking at. The following measure we use against data is accuracy, which is how well that data set actually reflects what is out in the real world. After that, we have availability as a measure. This is often one of the challenges I find for railroads around the world. This is how easy is it to be able to get access to this piece of data in the first place. It is quite common for railroads to store all of their data in silos, which actually makes it much more difficult for other divisions, other groups within the railroad to actually take advantage of those data sets. However, there is a huge wealth of information that can actually be used if we can actually open up these data sets so they can be shared between different asset disciplines. The next two measures are repeatability and reproducibility. These are subtly different measures of the quality of the data. Repeatability is if we take an asset and we measure it exactly the same way under the same circumstances several times, do we get the same result? Reproducibility is if we take this asset and we measure it in different ways under different circumstances, do we still get the same result? So reproducibility is typically a better measure of the overall quality of the data we're looking at. The other key item we need to look at is items such as the relevance of that data. We're not collecting data for data's sake, we're actually collecting data in order to derive information to make informed decisions. So making sure that we're collecting the right data in the first place, but with the correct currency, the correct completeness, the update rates appropriate to it, and the accuracy measures. Now we've looked at data, what we'll do is look at definitions of big data. There are a number of different definitions available for big data. The one that I prefer is the 5 V's for big data, which are volume, velocity, veracity, variety, and value. Volume is the one that people would most often associate with big data, which is physically the amount of data, the sheer volumes of data that we're actually trying to cope with in whatever system we're working with. However, that often isn't the biggest challenge that we actually face. The second of those V's is velocity, which is the rate at which data is coming at us. If we have a static data set, it can often be much easier to manage than if we've got continuous streams of data coming into us that we need to be able to keep on top of and actually keep up with. So that's the velocity challenge for big data. Veracity is often the biggest challenge that we actually have, which is how difficult is it to reach into that data set and start extracting the information that we need to find from it. So it's generally a function of how well structured and how well organized and how well understood the data is, and also of the quality of the data that's actually coming through to us. Variety is another challenge we often see in big data, which can be if we've got lots of different forms of data, then that can add to the complexity of extracting information, because it's quite common that the information we're looking for isn't a piece of data that's hiding inside the overall data volume we've got, but it's actually related to the relationship between these different data sets. I'll show a worked example of this in a few moments. And then finally, value. And value we can look at in two ways. It's actually the value of the data set, i.e. the cost of acquiring and maintaining that data set, but also the value of the information contained within it that can be extracted. And of course, the potential savings that we can actually make from being able to extract information and hence actionable items from data. Just as some simple examples of these, I'm going to look at some rough order of magnitude values for network rail operations and maintenance. So for volumes of data, there are, just for geometry data, in excess of 50 billion geometry samples that they actually currently have available to them that covers several terabytes. So we've got a large volume of data. In terms of velocity, there are over 50 million new samples per day that will come in from all of the different measurement vehicles that are actually traversing the rail network. Veracity, if we look at all of the data that's available against the network, it's a combination of structured and unstructured, subjective data, so from inspections, objective data from measurements, binary files that have been brought in, and there are various challenges with data quality and local data sets available, and be able to get access to those as well. Variety, if we look at just the track decision-making system, the data that gets fed into that comes from 13 source systems and is in excess of 60 data sets. And in terms of value, the budget that they're actually trying to manage by pulling all this data together is in excess of $2 billion per year of maintenance budget. So, we're looking at a data set that can actually have an influence on a very, very high value task being undertaken by the rail operators. I'm going to run through an example now showing what these 5 V's mean to us and how moving from data through to information through a big data process can actually start assisting us with increasing return on investment. But firstly, I'm just going to quickly talk about the diagram you can see here, which is the PF curve. So this is a curve that shows asset deterioration over time. So our asset is deteriorating from left to right. When we get to the right-hand edge of this curve, we get to a point where the graph hits 0. That is where our asset is physically broken. Just back from there, we've got an F. The F represents a point of functional failure. That is the point in an asset's life cycle where it is no longer capable of meeting its requirements. So in the case of track, for example, that could be a speed restriction that's being put in place. So it's still physically able to perform a task, but it's not fit for purpose for the requirements that are actually measured against it. Working our way further back in time, we've got a P point. That point is the last point in time at which we need to identify we are going to have functional failure such that we've got enough time to plan, schedule, and execute the corrective action that needs to take place. So what we actually need to do is look at all of the data that's available to us and identify the rate of deterioration of our asset so we can identify this P point in time to be able to schedule maintenance before we hit functional failure, hence increasing the availability of the railway asset that we've got, and in this particular example, increasing the overall value that we're getting from the rail asset. So I'm going to work through this example. The data we're looking at here is actually real data, but it has been obfuscated, so it's just a short length of track geometry data. This is actually the raw measurement data from 10 repeat samples that's been brought in up against the length of rail network. We're looking at about 200 meters worth of data here with 10 repeat samples. There's a few tens of thousands of samples. If you try to look at that, then we've got a high volume measurements may be coming in every few weeks or maybe every couple of months over this length of track, so the velocity isn't too high for it. But trying to make decisions just from that data set on what the quality of the asset is and how it's deteriorating is going to be a challenge to us. The first thing we need to do is start solving the veracity problem. And what we've done here is actually aligned all of those data sets against each other, so we can actually start seeing what the track is physically doing. The measurement we've got here is a measure of the vertical movement of the track. So it's a measure of the roughness of the track. So larger values equate to poorer ride quality, simplistically put. Now we've aligned these data sets, we can actually see where we've got track that is stable, isn't changing over time, and where we've got track where we've got localized points that are actually deteriorating over time. But what we want to know about is the overall condition of this track and how it's deteriorating, and at what stage we're going to need to step in and intervene against this length of track. So the next thing we're going to do is start trying to tackle the veracity problem further by deriving a quality index. So the screen we're looking at now is showing us time with the oldest dates at the bottom and the newest dates at the top. And what we've done is colored up in different blocks the quality index that we've derived from all of this measurement data that's come in. So this is now giving us a simpler way of visualizing the data. Leif is going to talk more about visualization of big data later on in the presentation, but this is showing us that green is good and yellow is satisfactory. Red track would be poor under these circumstances. So our track starts good, deteriorates to satisfactory, becomes good again, and then just starts deteriorating at the top, and we could read this as a graph going up in time. Next thing we're going to do is look at variety. So I can see my track is actually changing. It's getting worse and better. So I want to superimpose on top of that the maintenance activities that are being undertaken. So we're loading in this case, tamping and stone blowing activities that can identify how our track is. It started good, it deteriorated, we did some maintenance, and it improved. So we're starting to bring together these disparate data sets to, again, gain a better understanding of what's happening. Then we start trying to extract further value from this data. So we've derived our quality index. What we're now doing is we're saying, okay, I've got an index that's showing me how my asset is changing over time. I know when it was last maintained. Let's actually start running some trends through that to derive future conditions. So the values you can see here from yellow deteriorating through to a more reddish color are showing us the predicted future rate of deterioration of this asset that has been derived from that raw track geometry data. Once we've done that, we then need to start extracting the information that we need in order to start making informed decisions related to maintenance. So we've superimposed on top of there 2 lines, and these are our P and F dates from the P to F curve that I showed earlier. So this is the date at which we predict there is going to be functional failure, at which point we're going to have to put a speed restriction in up against this track asset, and a second date up here, which is the predicted date of true failure, the point at which we're going to have to shut the line. We can then go and validate that data. So we're actually looking now at a graph that's showing us time increasing in the x-axis, and the condition index that we've derived from our raw data deteriorating in the y-axis. So the higher the values you see, the further up the screen we are, the worse the quality of the asset. So we can see over time our asset deteriorated. A maintenance activity, the blue line, took place as improved. It then deteriorated further, and it's predicted to carry on deteriorating out like this into the future. What we've actually chosen to do here is make sure that the information we're deriving, i.e. the quality index and then the deterioration, is chosen in such a way that it's going to give us meaningful data at the far end. So we've chosen to derive a quality index from our raw data that will demonstrate linear deterioration, which makes it easier for us to extract that information out at the tail end of the process. Once we've actually got these predictions of the dates at which we're going to go through our maintenance and safety thresholds, we can put these into a tabular form, and then once they're in that tabular form, they can go through into work order management systems, work bank planning, to be able to make sure that the work that's being performed is actually scheduled in before we hit any of these dates. So this is showing the process that we've worked through, that we've started with our raw measurement data, and then we've tackled each of those 5 V's in turn, finally trying to get to a point where we can get some value out of that data set, or out of that combination of data sets, that can then subsequently be used to make more informed decisions about the maintenance for the track assets. The example that I just showed was actually of track geometry. We can show exactly the same thing, for example, for rail wear. These are both related to linear assets, but the same principles actually apply to kind of discrete assets, to rolling stock, to switches, items like this as well. So the example we're now looking at, we've got a length of track. The data set across the bottom is actually showing us head loss. So this is actually the rate of wear of the top of the rail. That raw data set with multiple scans drawn on top of each other is actually quite difficult to interpret and to be able to make any decisions against. So what we've done is gone through a similar process and derived an index against that, cleansed the data, derived the index, and then visualized it in such a way that it's easier to understand what the track is doing. So the track here has been chopped up into straights, transitions, and curves. And then for each uniform curve here, for example, we can see green is unworn track, wearing through to red is fully worn or life expired track. So it's easy to visualize the current state of our track, which is the latest recording that we have, predict out the future rates of deterioration, and then come up with those derived values in terms of when our track is going to be life expired, and then look at that in terms of the view we have here, year on year, which means that we can look at, the amount of, in this case, rail replacement we're going to need to do in 2018, 19, and 20, just to make sure that there are no surprises coming up, and we can actually start balancing the renewals that we need to do. So if there's a particularly large amount in 2020, we can pull some of that forwards a year. We can also look for places where we've got excessive deterioration rates associated with these assets as well, or places where the theoretical deterioration model doesn't match the observed deterioration model we've got, and start flagging that up. So this is combining the big data we've got with theoretical models in turn to be able to extract further information, is where we're varying from the norm more than we should. It's worth pointing out as well that when you're looking at big data, especially data about something that is changing over time, there is a huge value to storing a rich history of that data, as rich a history as you can actually store, because that historic data is all of the information about how you got to where you are. The way I like to look at this is what we want to do with a data set is be able to do 3 things. Firstly, in terms of a timeline, I want to be able to look down and say, where am I now with my asset? What's all of the data I have and all of the information I can derive about the current state of my asset? The second thing I want to be able to do is look into the future and say, how is this going to change? How is this predicted to deteriorate or improve over time, so I can actually start planning and scheduling to make more informed decisions? But the third thing I want to do as well is look back into the past and say, how did I get here? What are the things that have happened to my asset? What are the changes, good and bad? Which means when I'm trying to plan anything I'm going to do in the future, I can learn lessons from what's actually taken place in the past to be able to try and not repeat mistakes that have been made previously. What I'm going to do now is hand the control over to Leif, who's going to run the next portion of the presentation. So Leif, over to you now. If you could share your screen, please.
Okay, thank you, Andrew. I appreciate the handoff and a lot of good information there. I'm going to give it a second to make sure my screen is showing for everyone, and then go ahead and continue. So in addition to the operational information and test information for the data about our assets, I kind of wanted to expand the discussion to really look at more of the information about the assets in addition to the data, and talk about the information silos that are pretty common in today's world. So in the case of our systems, we have a lot of different software solutions that are specialty applications that manage information about our assets, but each of these systems operate independently, really. And from an engineering document management system to a work management system purchasing, the operational and data systems for operational monitoring and test data that Andrew described earlier, as well as the information for safety and compliance, project management, and so on. Each one of these systems has their own repository of information. The issue here is some of that information is redundant, and trying to keep that information in sync is very difficult, as well as having visibility into information that's related to each other. So let's say, for example, we have our engineering document management system, and we have a new design that affects an area of our out in the field, and we're specifying a new piece of equipment. And then on the procurement side, we have a purchase order issued for that piece of equipment. But somewhere down the line, there's a change to the design. The issue is that if the procurement system isn't aware of that, or say the work management system that's actually going to install that piece of equipment isn't aware of that change, we could risk purchasing a piece of equipment that is no longer relevant, or scheduling work to be performed out in the field that is no longer applicable. So the issue with that is trying to tie all these systems together and relate all that data, that volume of information together so you have a complete picture is exceedingly difficult. And because of that, we end up having these information silos where we don't really have a good idea of what the impact of any changes or the relationships of the information to see the complete picture about that asset is really difficult. So one of the approaches is really to create a digital representation or a digital asset, and from that digital asset relate all that information by building that digital twin of what is actually out in the real world. And by doing this, instead of trying to make all these systems talk to each other, we can take that digital twin and be aware of, hey, if I go in and I look at that asset, I can see, hey, there's a work order issued against that. Oh, there's a change request issued against that. I have operational information. So now I can actually see that inspection data, all that other data through the use of that digital twin. The critical piece is that digital twin needs to stay current and needs to accurately represent what is out in the field. And by linking all that information together, we now have a complete picture in context of that asset. And in addition, what we do is because we have those relationships, we're able to see that asset in context to all that other information, regardless of whether it resides in your engineering document management system for the design data, or it resides in your change request system for changes. So now, whether you're looking at a piece of information through that digital twin, you can go at it from a lot of different ways. So say, for example, I'm looking at my requirements. I can see that requirement drives the design for this particular asset. I can see that requirement is specific to these people who are responsible for compliance and so on. But if I'm out in the field, I might be more asset-centric. I might be looking at a particular asset, say a pump or a motor, and I want to view, not only do I want to view the information about that pump as far as, its operating requirements, but I also have access to the maintenance information, the documentation in my document management system. I also have information to the engineering drawings, all by looking at that asset. So if I'm going out in the field to do work on that asset, say maintenance, say, as Andrew showed, if we're predicting failure and we need to do maintenance or replacement, I can then do a search for that asset. I can see the work manage or the maintenance instructions or the replacement instructions, all the drawings associated with that, all through that single view of that digital asset. If I'm more project-centric, now I can get a status of ongoing changes. So if I go in from a project view, I can see here's all the proposed changes against them. I can status all that. I can see if we're on schedule for the project, all because I'm able to relate all this information together. So taking this a step further, I wanted to talk about how we present that information, because if we have all this data, it's overwhelming. right? So we come in and we see, all the test data and operational information. Andrew showed how we can parse through that and present that in a meaningful way to predict failure. But we also need a way to navigate that information and visualize that information. One of the directions that I see this going is really leveraging our 3D data. So we've talked about textual information, but how can we take this data and really leverage our 3D models? So the first thing I want to show is, in this case, I'm showing a facility, right? So I want to navigate the model. And again, I think this is really the direction that we're going to leverage information and navigate information. So think of this from a user perspective. I can come in, whoops, sorry, I advanced too soon. Let me go back. So we can go in and we can navigate this data. Now the nice thing about navigating the model is everyone is familiar with graphical content. A picture is worth 1,000 words. This is very easy to understand. And I think navigating graphically is a natural progression. But right now, we need a way to overlay the data that we have. So what you see here is I have a graphical representation, the digital representation of what's in reality. I can rotate, I can zoom in, zoom out, and then I can navigate to the asset I'm interested in. So in this case, I'm going to go look at a vessel, and when I select on that vessel, I can see all information that is linked to that asset. So now on the right-hand side, I can see, by overlaying that data, I can see the operational information, I can see any of the related documentation, which we'll show in a minute, but I also can overlay operational information, such as operating temperature and pressure for that vessel. And if you think about this, if I set a max or a minimum condition on that asset, I can then highlight that asset to draw quick attention to say that this pump is, or this vessel is over pressure. But I also see this information over time, so I can see trending information about that. Then if we go in and we can go in and again search all the information that's coming from a variety of systems for that metadata. Now, in the case of the 3D model, it's nice in certain situations where we have access to this information through a 3D model. But in some cases, when you have an existing asset, building a 3D model is not always practical, right? So when it comes to a kind of a brownfield scenario, what we have is the need to represent that information quickly and easily, and building a 3D model of existing assets isn't necessarily cost effective, and it's very, very time consuming. So what you see here is leveraging a variety of information to build what we call a reality mesh. So this is an existing facility where we've leveraged point cloud data, laser scans, digital imagery, and photogrammetry to build this mesh. And while the granularity here isn't the best that we're capable of, keep in mind that this was taken over the course of a couple hours, versus building a 3D model can take weeks or months to build, if not longer. So here what we've done is we've taken this reality mesh and we've tied it into the data. So when I select an asset, I have, again, all that information on the right-hand side that could be coming from a variety of systems, and I can go ahead and view that data. And I can drill down to actually view relationships to the documentation. So remember how I showed earlier in the presentation, we had documents and drawings in our EDMS, or our engineering document management system. We had change package information. I could have inspection information, and all of those documents are available through this view. Moving forward, we can go ahead and review that drawing for whatever reason, or if I was looking to do maintenance on that, I'd have access to those maintenance instructions. If I had inspections, I could view that data as well. Now, building this is actually pretty straightforward. Once you have the information from that reality mesh, I can start to add intelligence or overlay that data on the graphics. So this is an example of how we do that for a pipe. So I'm going to go in and I'm going to draw a polygon around the pipe that I want to tag to my asset registry or my asset library. So I'm just going to go ahead and draw this, and because of the model, it's smart enough to identify all the geometry within that boundary that I specified. But it's not smart enough to necessarily know if I'm interested in the supporting structure or something else. So what I can do is I can specify the z-axis to really narrow it, and it identifies that pipe. And now I can go in with my asset library and actually relate it to the physical asset information. So in this case, I'm identifying the pipe, and now with that mapping, I can select on that pipe and I can see all the other data that's already built up in my information management system. Now going forward, leveraging that information, you can see that by selecting it, I have all the attribute information. But as I build this rich data environment overlaid on my geometry, I can actually quickly do searches. So if I'm searching for a particular asset, I can specify what type of asset. So if I want to see all the containers that have been identified, I can quickly do that, and then I can select. And again, I'm navigating visually instead of relying on textual information. If I'm looking for a particular vessel, I can quickly do that as well. And now, just like before in my 3D model, I can highlight that vessel, I can view the operational information, and so on. So what I really just wanted to talk about was just showing the ability to leverage the graphical information and overlay the data that we have to make it easy to navigate to that information and consume that information. So by leveraging the graphics, it's something that a wider audience or a wider variety of stakeholders can leverage to view the information that's important to them. And with that, I think I'll hand it back over to Andrew to summarize what we've discussed.
Wonderful. Thank you very much, Leif. Could you just click a couple of times to get the text to appear on the last slide? So, yeah. In summary, if we're looking at maximizing return on investment, the things we need to think about, firstly, the data that we have is expensive to collect. Generally, it is already being collected as well. A lot of this data already exists inside organizations. So what we're trying to do with big data is actually take full advantage of all of the data that we've got, bring it together and understand all of the information that can be extracted from it, not just restrict it to the purpose for which it was initially collected or it's actually being brought in. That data is often difficult to interpret. So what we need to do there is actually process it to generate information, and then also focus on the visualization, the user experience we have to make it easy for people to be able to interpret or actually do things with the information that comes out of the far end. This data is often difficult to access. It often sits inside silos. There are huge advantages to gaining data mobility, so we can actually have that data shared and reused between different divisions, between departments, and through the life cycle of assets as well. The savings that people are quoting from the BIM processes of the order of 17.6%, I believe, over asset life cycle. Any decisions that we make are only as good as the information that's being used, which is absolutely critical. So making sure that the data that we have in turn is of a known quality, which means that we can understand the bounds for the information we derive from it. That in turn gives us a confidence level for the decisions that we're actually making. So what we've talked about over the course of this presentation, it's a huge topic to cover in half an hour, but is a look at what data is, what issues data can actually have, why we need and use data, what big data is in particular and what makes it different from normal data, running through a simple worked example of from the definition of big data of how you would transform that through into information, looking at the scope of data, and then looking at the importance of the ability to visualize that data and the resulting information to be able to help end users make decisions or perform actions that can actually improve the ROI for the assets that we're looking at. That concludes the formal part of the presentation.